Ms. Susan Tennant. I'm part of the Learn America team, and we've prepared this mathematics review to help you succeed in your nursing program. You've each received the results from the math portion of the recent diagnostic test that you took, where your strengths and your weaknesses were identified by topic. This will be the first of 4 two-hour lectures. The lectures are designed to present various mathematical content and improve your math skills so that you see where you need the strengthening, and we hope we will provide that strengthening for you. You may find there's not time to deal with all the questions that you have during this presentation. Don't forget that we've scheduled online follow-up sessions. During the 2 weeks that follow each lecture, I'll be holding 4 one-hour online sessions. During these sessions, you have the opportunity to ask questions about the topics we've covered today in the lecture, as well as any other problems you may encounter from the Check Your Understanding sections. Now, going forward, you should know that the class notes that we're using in the lectures will be uploaded prior to the lecture so that you can choose to download a copy and you can add comments that way throughout the presentation to help you remember. So you don't have to actively take notes while I'm giving this presentation. You can just concentrate on listening. Now, please consult the review schedule that's been sent to you for the upcoming lectures and the online help sessions so you know exactly when they'll be taking place. I also want to urge you not to feel embarrassed to ask questions. That's one of the ways you learn, and that's why we're here. We're here to help you. And I'm going to be asking questions too, because we're using new technology here and it's new to me. And you may have experienced it already if you're taking part in the biology program. But I'll have to ask your indulgence because this is the first time I'm using it. So I may hit some bumps in the road and may have to send out SOS signals to our tech team here from time to time. I ask you just to be indulgent of that. Remember that all of us here at Learn America look forward to being part of your success at LIU. Before we get started, please be sure your video is turned off and mute your audio. And so now good luck, and let's get started with the program. We start with something very basic, just numbers and operations. The first thing we look at is working with sets, setting up our vocabulary and our definitions. What is a set? Well, a set is a well-defined collection of objects or elements. Now, well-defined is very important because if it's not well-defined, we don't know how to put it in the set. So supposing A is a set of all letters in the word mathematics. Well, this is a well-defined connection. We know what those letters are, so it's a set. But supposing we say, well, take the collection of tall students in the class. Is that a set? Well, it's not well-defined because different people have different ideas about who's tall and who isn't tall. So B is not a well-defined situation, and therefore we can't say that B would be a set. Now, we represent the set in a couple of different ways. One way is called roster form. In this form, all the elements of the set are actually listed, separated by commas and enclosed by brackets. So, for example, the set of vowels in English alphabets is written in roster form using braces A, E, I, O, U. Now, we don't repeat elements. So, for example, if we wanted to write in roster form the elements of the set mathematics, we would put in an M, the A, the T, the H, and then the E. But now notice again, we have an M. We don't repeat that. We have an A, we don't repeat that, and a T, which doesn't get repeated, because those are already in there. But then we have an I, a C, and an S. So this would constitute the set of elements in the word mathematics. We can also write sets in what we call set builder form. In this form, we describe the elements of a set by means of a statement. So we might say, for example, the set of all even integers that are greater than -5, but less than 5. If we were to write this in set builder form, we write it as shown here. And this is read, the set of all x such that 2x is in the set of integers. Notice z is used for integers. and x is greater than or equal to -2, less than or equal to 2. Or you can also read this -2 is less than or equal to x, which in turn is less than or equal to 2. So let's consider set A consisting of the letters in the word number. We denote that n is an element of A by this notation, n with a little like kind of Greek E sign, and that is an element of A. Similarly, U is in the set, so U is an element of A, M is an element of A, B is an element of A, E is an element of A, and R is an element of A. Now, consider A and B as two different given sets. If it turns out that every element in set A is also an element in set B, we then say A is a subset of B, and this is the notation we use. You can kind of think of it this way. This is like a C, so it's sort of A is contained in B. If you see the bar under it, it means that A could actually be as big as B. Now, if A is not a set which contains all the elements of B, in other words, if there's at least one element in B which is not in A, then A is a proper subset of B, can't be equal to it, and so we just show the contained sign without the equal. A is a proper subset of B. Now, consider the following sets. A consists of the elements A, E, and I. B consists of A, B, C, D, E, F, G, H, I, and J. Notice, every element in A is also in set B, and B contains elements that are not, I think we have a little error here. B contains elements that are not in A, is what we should have. Whoops. So A is a proper subset of B. A is contained in B. Now, consider a set D. When we talk about the cardinality of a set, we're talking about the number of elements in the set. So if you look at set A above, set A consists of 3 elements, so its cardinality is 3. If you look at B, it consists of 10 elements, so its cardinality is 10. If we have a set that has a finite number of elements, in other words, a finite cardinality, the set is called finite. If it has infinitely many elements, then we say the set is infinite. So for example, if we look at the set of vowels that we have here, C, A, E, I, O, U, it's a finite set, its cardinality is 5. But if we consider the set D, where D is, say, an odd natural number, remember natural numbers are counting numbers, D is an infinite set. If 2 sets have the same number of elements, then we say they are equivalent sets. Now, we have various ways of representing sets. One of the ways that we represent them, of course, you've seen already by listing, but we also like to have pictures. Pictures always make things very clear. So one of the chief ways that we show sets using pictures is by means of what's known as a Venn diagram. The Venn diagram can be used to indicate the relationships between the sets that we're considering. So generally what we do is we create a universal set. In other words, that's everything possible. That's U, the universal set. The set we're interested in is generally shown as being inside the set. And normally the kind of strategy that's used is we show the universal set with a rectangular shape, and then we show sets within it using circles. So here we have set A as a set contained within the universal set. Now the stuff that isn't in A is considered to be the complement of A, and that would be everything that's shaded here that is not in set A. The complement is shown using the notation prime. So the complement of A is A prime. So let's consider how this works. Supposing the universal set contains the elements we see here, all the counting numbers from -5 to 5. And let's let B be the set containing only the elements -4, -2, 0, 2, and 4. Okay, that in effect takes out from our set these elements. But now what are we left with? Well, we're left with -5, -3, -1, 1, 3, and 5. So the complement of set B, written B prime, is the set -5, -3, -1, 1, 3, and 5. If we were representing this in terms of Venn diagram, the set B would be the one that we would have in the circle, and the complement of B would be everything outside within the universal set. Now, there's also terms that we need to know: union and intersection. These are very important. The union of two sets or more is a set of all the elements that are in either one or the other or both. The symbol for set union is U. So and that's kind of obvious, U for union. So if we have the union of sets A and B, we would write A union B. If you look at the diagram, you can see that we have set A here, we have set B there, and everything that's in A or B or both is shaded. That's the union of the two sets, A union B. Now, the intersection of two sets are only those elements that are common to both. So if you look at sets A and B again, the parts that are common to both are only the overlap here. That little line shouldn't be there. So just the overlap is the intersection. The intersection is shown like the upside down U. So the intersection of sets A and B is written A with this symbol like an upside down U, B. So consider the following example. Supposing that we use, whoops, how did I do that? How do we go back? Okay, got back. Okay, we let U be the set of natural numbers that are less than 10. Okay, let set C be 1, 2, 3, 4, 5, and set D consist of 4, 5, 6, 7. Now the union will be everything in both. So that's 1, 2, 3, 4, 5, 6, 7. The intersection will be only those elements that are in both sets. Now look carefully, you can see 4 and 5 are in set C, 4 and 5 are in set D. Those are the only elements they have in common. Therefore, C intersect D is a set that consists of only the elements 4 and 5. Now, if sets have no common elements, they're said to be disjoint, and their intersection is said to be empty. We call the empty set, notice like a set with nothing in it, also the null set, which is actually the Greek letter phi. A common error is to write set notation with phi inside. Don't write the empty set that way. It's wrong, because what that says is that we have a set and it contains something. It contains the empty set. So we do not write that. We write only open brackets for empty set or the Greek letter phi. Now let's consider the following. Let U be the set of all natural numbers. Remember, those are the counting numbers. Let N be the set of all even natural numbers, and N be the set of all odd natural numbers. The union of these two sets, of course, are all of the numbers, but the intersection is the empty set because the evens and the odds have no elements in common. So the intersection of M and N is the null set written by the Greek letter phi or showing brackets with nothing in them. Now we're going to try to look at numbers and consider how they are classified. Many, many different ways of classifying numbers. Mathematical sets are classified generally as we will be showing here. First of all, the numbers you first learned when you learned to count. We learned to count, we call them counting numbers. Start with 1 and count by going up, 1, 2, 3, 4, 5, etc. These are also called natural numbers because they really are the most natural way that we would tend to count. The whole numbers consist of all of these natural numbers with 0 added into the set. So the elements of the whole numbers are all the natural numbers and then 0 in addition. These are designated by the letter W. The integers, generally designated by the letter Z, consist of the natural numbers, 0, and the negatives of the natural numbers. So every whole number is an integer, and the integers, you will have to remember Z, okay, consists of the whole numbers and the negatives of the natural numbers. Now, the rational numbers, which are the next set, I kind of have funny thoughts when I think about the rational numbers, because when I was a student, nobody bothered to explain to me, and I guess I didn't figure it out for myself, that the name rational came from ratio. And I knew the English word rational meant that you were kind of sane and normal, and irrational meant that you were kind of crazy. And I thought rational numbers were sort of sane, normal numbers, and irrational numbers were kind of crazy numbers, and I didn't really realize that that wasn't what it meant at all. What rational numbers means is that numbers can be expressed as ratios. You can see the term ratio in the word rational. And we'll be also looking at irrational numbers, which simply means they are not the rational numbers. So it has nothing to do with craziness. It has to do with ratios. And the set of rational numbers are denoted by the letter Q. For quotient, rational numbers can be written in the form P over Q, where P and Q are integers, and Q is not equal to 0, because remember, you can't divide by 0. The letter Q is used because a rational number is a quotient. Now, what would then constitute the set of rational numbers? Well, every integer is a rational number. For example, 8 could be written as 8 over 1 or 16 over 2. Every decimal number that ends, that terminates, is a rational number. So for instance, if we have 0.175, which is the same as 175 thousandths, this is a rational number. And then every non-terminating, which means non-ending, repeating decimal is a rational number. So numbers like 0.3333 or 0.545454, where you have a steady repeating pattern, even if it doesn't end, as long as the pattern is the same and it repeats, that is a rational number. Now, if both P and Q have the same sign, that is both positive or both negative, then the rational number is positive as well. If P and Q have different signs, that is one is positive, one is negative, then we have a negative rational number. Now, we spoke about the irrational numbers. Now, this simply means the numbers that are not capable of being expressed as ratios. They are not part of the set of rationals. They, with the rationals, make up the set of what we call real numbers. So the real numbers R minus the rational numbers Q give us Q bar, which is really the irrational numbers. Number is irrational if it cannot be written in the form P over Q, where P and Q are integers and Q is not equal to 0. So, for example, numbers like pi, radical 5, 0.121221222, the things you see on your screen, these are irrational numbers. Now, you might be very tempted to think that that last one is rational because you can see what the pattern is. There is a definite pattern. The key is it's not the same pattern. It has to be the same pattern repeating. So even if you can figure out what's going on and there's some sort of a logic behind it, it's not rational unless it's the same pattern that repeats indefinitely. Together, the irrational numbers and the rational numbers make up the set we call real numbers. Real numbers totally consist of all rational and irrational numbers. And if you want to graph them, you can graph them on a line, and they completely fill the number line. Nothing else can get in there. Nothing else can get in there. No other numbers of any other kind can fit on the number line. The real numbers completely fill it. Now, we also have a set of numbers called complex numbers. These we will not be spending too much time to look at right now, but you'll probably be looking at them sometime in the future. The complex numbers encompass all the real numbers. So for example, if you look at this diagram, you see that the natural numbers are contained within the whole numbers are contained within the integers are contained within rational numbers, and then irrationals are separate. Now, the diagram's just a little bit misleading because it gives the impression that there's something in the set of real numbers that doesn't fall into the rational or irrational category. That's actually not true. Just to make the diagram, well, a little clearer that irrational are part of reals, rational are part of reals, it's drawn that way. But if we really wanted to represent the way the real numbers are, what we have to do is just consider this and get rid of this. It was done to be pretty, really. But those two sets together, that make up the real numbers. And then the complex numbers encompass everything. The null set or empty set, remember, is denoted by empty brackets or the Greek letter phi. This is the set that contains no elements or members. And then the universal set, which is everything that we're looking at in a given situation, is denoted by U. Okay. Now, if you're not out of breath by now, with all of that terminology, now we're going to look at how we combine these things, how we operate on these numbers. Of course, you're already familiar with most basic arithmetic operations: addition, subtraction, multiplication, division, probably also finding square roots and finding absolute values of numbers. Most of the operations that we do are falling into the category known as binary operations. Binary means two, and most operations that we do are on two elements at a time. Even if you have a long list of things, for example, that have to be added, you do it two at a time. So an operation on a set is a rule that relates two of the elements or numbers in the set to produce another element or number in the set. So for instance, we add numbers, we add them two at a time. We subtract them two at a time, and so forth. So these are all binary operations. Addition, subtraction, multiplication, division are all binary operations. Now, I'm sure many of you, I know I encounter this all the time. I go on Facebook and somebody's got something on there. What's the answer to this problem? And they've got a whole bunch of numbers with different things, multiplications and square roots and powers and so forth. And then you see an astonishing number of responses with all kinds of different answers. And I always think, oh boy, we're really not doing a very good job educating our students if they come up with all these different answers to this problem. Because there's only one way to do it. We all agree. We have to agree, otherwise we come up with all kinds of different answers. We have to agree that there's going to be a way we do problems so that we all get the same result. And that if I do an arithmetic problem on this side of the world, somebody doing the same problem on the other side of the world is supposed to come up with the same answer. Okay, so the question is then, what are the rules? And then to evaluate an algebraic expression, we follow these rules. The rules are known as the order of operation. We follow a uniform procedure that guarantees that we all come up with the same answer in exactly the same way. So these are the rules that we follow. First, we look and we simplify all the expressions within parentheses. Then we evaluate all powers or exponents. After that, we go through from left to right, performing any multiplications and or divisions that we encounter. And finally, additions and subtractions, working from left to right. Now, you probably have encountered this before, and maybe you learned a little mnemonic device or trick to remember it. Please excuse my dear Aunt Sally, or PEMDAS. We have parentheses first, then exponents, then we have multiplications and divisions, the M and the D, and then addition and subtraction, the A and the S. Follow these rules, we all come up with the same answer. So if we look, for example, at the first problem, evaluate 21 minus parentheses 5 minus 2 squared. Well, first we do the parentheses. So the 5 minus 2 squared gives us 3. Then we do the power. So we have 3 squared, which gives us 9. So finally, we have the 21 minus 9, which gives us 12. A very straightforward way that we follow the rule. Everybody's got to come up with the same result. Now, if we're asked to evaluate an algebraic expression, one that involves letters or what we call a literal expression because it involves letters. We have values for A, values for B. We put these values into the expression and then we follow the rules. So substitute the values for A and B in the expression and then follow the rules to evaluate, okay? Parentheses first, power, and within the parenthesis, notice you have to do the power, adding those together and multiplying by the -2, and finally come up with -24. Next, we're going to take a look at how we represent numbers on a number line, okay, what we call graphing. The number line is used as a visual representation for the set of real numbers. Every real number corresponds to a point on the line. Every point on the line corresponds to exactly a real number. We call the number that corresponds, the point that corresponds to the number, its coordinate. This is known as the completeness property. Remember, we said the real number line is completely filled with real numbers. They are complete on that line. Of course, you may then ask, well, you spoke about complex numbers. What do we do with those? Well, we've got to find another place to put them, but right now we're not going to worry about that, but they can't go on the line. Only real numbers can go on this line. When we graph a set of numbers, it means we locate them on the number line. The origin is the point associated with the number 0. Points to the left of the origin are negative. Points to the right of the origin are positive. If we have any two different numbers on the number line, the number to the right is bigger than the one to the left. So, for instance, take the set of numbers, say set A consisting of -2, 0, 1.5, 3, and 4.3, and we graph it on a number line as shown. You can probably see these points pretty well. I hope you can. There's the -2, there's the 0, there's a 1.5, and there is 3, and here's the 4.3, which of course we have to estimate. And notice that as we move to the right along the number line, each number that is to the right of another is greater than that number. So 0 is greater than -2, 1.5 is greater than 0, and so on. Now the integers, we've spoken about those already. We denote those by the letter Z. The integers are denoted by the natural numbers, 0, and the negatives of the natural numbers, as shown in this representation. The set of numbers that are usually, these are the set of numbers that are usually used to name the points on the line. So if we want something in between, we tend to estimate them, and we denote the points using integers. Positive integers to the right of 0, negative integers to the left of 0 on the number line as shown in the diagram. Okay, now, how do we operate with these integers? Well, we want to know how to add and subtract. We want to know how to multiply and divide. Adding integers, well, if they both have positive signs, when we add them together, we're going to get a positive number. If they have if the two integers have negative signs, then again, the sign of the sum will be negative. So the only time this really kind of gets interesting is if the integers have different signs, because then the sign that dominates will be the one that ultimately winds up as the sign of the answer. So for example, if you are trying to add a -4 to a +3, you can think of this as starting at the origin here and then moving to -4. From that point, you're adding back 3. So the net result is that you've moved from where you started to -1. So that would be the net result of the addition problem. The ray in blue represents the sum having its endpoint at 0 and going to the tip of the arrowhead of the second ray. Now, if it turns out that the addition gives you a ray that moves to the right, then the sum is positive. If the ray moves to the left, the sum is negative, and the length of the ray will represent the number of units in the answer. For subtracting, one of the easiest ways of thinking of subtraction is just think of subtraction as addition of the opposite. So you subtract two integers by changing it to an equivalent addition problem. So for example, if we want to subtract 11 from 6, we can think of this as 6 added to -11. And of course, if you think of going 6 units to the right and then 11 units to the left, your net result is going to be that you've moved 5 units to the left from the origin, and that would be the result of the subtraction. So subtracting 11 from 6 is the same as adding its opposite, that is -11, to 6. Now, how do we demonstrate subtraction? Well, again, subtraction is like the addition of the opposite. So supposing we're trying to represent 3 minus a -5, or 3 subtract -5. We see that if we start with 3 on the number line, and then we start from the 0 again and go -5, the net result is that we've gone a total of 8 units. So starting at 0, draw a ray with the endpoint at 0, arrowhead stopping at 3. The ray goes to the right, of course, because the 3 is positive. A second ray starts at 0, arrowhead stopping at -5. Ray goes to the left because 5 in this case is the negative. The ray in blue represents the difference between the two, and this has its endpoint starting where the second ray ended, goes to the point where the first ray ended. So if the ray moves to the right, the sum is positive. If the ray moves to the left, the sum is negative, and the length of the ray represents the number of units in the answer. Now we want to look at the multiplication and division of integers as well. And we multiply integers with positive signs. The sign of the product will be positive. If both are negative, the sign will be positive as well. But if they have different signs, the sign of the product is negative. Now, one of my colleagues has a very cute way of thinking about this, and I hope I can get it right. But what she says generally is if you have, say, a good guy here, and a good thing happens to the good guy, so you have a plus for the good guy, and then you have a good thing happening to the good guy, which looks like a little difficulty writing on this screen. The end result is that that's a good thing, so that's positive. Now, if you have, whoops, how do we do this? Okay, you have two with negative. You have a bad guy and a bad thing happens to the bad guy. Well, that's good. So the result is positive. Now, on the other hand, supposing you have a good guy and then a bad thing happens to the good guy. Well, that's not good. So that result is negative. But supposing you have a bad guy and a good thing happens to the bad guy. Well, that's not good either. So that result is negative. So that's kind of a cute way to think about the multiplication of integers. Now, division works the same way because basically division is multiplication by an inverse. So it'll be the same. If you're dividing integers where both are positive, the sign of the quotient will be positive. If both are negative, the sign of the quotient will be positive as well. If they have different signs, the sign of the quotient will be negative. Now, we spoke before about what the set of rational numbers were, that they were numbers that could be represented as ratios, hence the term ratio here in rational numbers, and that they could be denoted by the letter Q, which reminds us Q for quotient. Rational number can be written in the form of a quotient, P over Q, where P and Q are integers, and of course Q can't be equal to 0 because you can't divide by 0. So examples are rational numbers, 2 over 5, negative 6 over 5, and every integer is a rational number because it can be written as itself over 1. Every decimal that ends is a rational number. So if we look at, for example, 0.156, we can write that as 156 over 1,000, again, a ratio. A non-terminating repeating decimal, that is one with a set repeating pattern, is a rational number. Now, we don't have to go into how we work this out right now, but for example, if we have 0.5555 and that goes on forever, that can be written as 5 over 9. You can check it out, by the way. Put 5 over 9 in your calculator and see what happens. Properties of rational numbers, that is, numbers which can be written as ratios. This screen summarizes the properties of the rational numbers. You'll see on the left, we have the density property, closure. The rational numbers are associative over operations of addition and multiplication. They are commutative over operations of addition and multiplication, and there is a distributive property of multiplication over addition. Now, don't panic because we're going to discuss what each of these means. This just summarizes them so that you can go back and take a look at this and remember what they are. Also, we will look at additional properties that we have for the rational numbers. We have a multiplicative property of 0, an identity element of 1, then that would be for multiplication. We also have an identity element for addition, which is 0. Every element except for 0 will have a multiplicative inverse. Every element will have an additive inverse, and then we will look at the multiplicative property of -1. So let's move on and look at these properties in more detail. What this means is really exactly what it sounds like. The rational numbers are dense. That is, for any two that you might select, you're going to be able to find at least one lying between them. Now you might say, well, how do I know that that's the case? Well, for example, consider any two. If you average them, that number is going to be between them. And that will also be a rational number because you're taking a rational number and you're dividing it by 2, thereby getting another rational number. The property of closure means that if we do an operation of either adding or multiplying on rational numbers, we always wind up with a rational number. So the set is closed. You can't get out of the set of rational numbers. The sum of any two rational numbers will produce another rational number. The product of any two rational numbers will also produce a rational number. Now, the associative property exists for both addition and multiplication. If you think of association, when you associate in a group, you group together with people. So the associative property is really a grouping property. And what it tells us is that we can change the grouping without changing the meaning of the expression. So for example, you take any rational numbers, say A, B, and C. If you add A to the sum of B and C, you'll get the same result as if you first add the A and the B and then add the C. So this is an associative property for addition. Now for multiplication, the same thing holds. If you take A and you multiply it by B times C, it will get the same result as if you first multiply the A by the B and then multiply by C. So changing the grouping will not change the result. Now notice we didn't change the order. The order or change in position would occur under the next property, the commutative property. Now remember, when you commute to work, you go back and forth. Commutative property for addition and multiplication tells us, in effect, we can go back and forth and we're still going to get the same result. So for rational numbers A and B, A added to B is going to be the same as B added to A, or A multiplied by B is going to be the same as B multiplied by A. Now, the distributive property is really very important, and keep in mind that the distribution works over the operation that is really one below in the order of operations. So remember that multiplication and division are done before addition and subtraction. Multiplication distributes over addition. It does not distribute over itself. So we always have to go down a level. Any rational numbers A, B, and C, A multiplied by the sum of B and C will distribute. So we'll have A times B plus A times C. And finally, we have an additive identity element, 0. For any rational number, if we add 0 to it, we don't change the number. So A plus 0 is A, and 0 plus A is also going to be A. We have a multiplicative identity element as well. This is 1. 1 does not change the identity of the number. So for any rational number A multiplied by 1 is going to just give A. And 1 multiplied by A is also going to be A. So you see there's an identity here in the sense that A does not get changed. It's identical to what we started with. We have a multiplicative property of 0. Any rational number multiplied by 0 in effect gets wiped out. A times 0 produces 0, and 0 times A is 0. Also, a multiplicative property of -1 changes any rational number to its opposite. So A multiplied by -1 and -1 multiplied by A, both are going to produce the opposite of A, or negative A. Now we have inverses for addition and for multiplication. Every rational number will have an additive inverse. So if we have a rational number A, there's going to be a rational number the opposite of A, which when added to the original gives you 0, the identity. Always keep in mind that the operation will produce the identity when you're adding inverses. So A added to -A produces the identity element 0. You can consider these to be opposites of each other. Multiplication, we also have an inverse except for 0. Okay, so for any rational number A, as long as A is not 0, there will be a rational number 1 over A, which you can think of as the reciprocal of A, where A multiplied by 1 over A will produce the identity element, which for rational numbers is 1. Okay. If you have a rational number A over B, where B and A are both not equal to 0, then there's going to be a rational number B over A, which operates as the multiplicative inverse. So A over B times B over A produces the identity element for multiplication, which is 1. Now let's take a look at some problems. First question. Let's find the additive inverse and the multiplicative inverse of -1/3. Now take a moment to think about what you think the answers might be. Okay. The additive inverse, remember, is going to be the number which, when added to -1/3, is going to produce the identity element 0. So the additive inverse of -1/3 is +1/3 because -1/3 added to +1/3 produces the identity 0. The multiplicative inverse of -1/3 is going to be -3 over 1, or simply -3. Here again, if we check it out, -1/3 multiplied by -3 over 1 produces the multiplicative identity, which is 1. Okay, let's look at the properties that are listed below and see if we can identify them. First property, 2/5 plus 0 is 2/5. Second property, if we group 2/7 with 3/4, and I'm kind of giving you a hint here, and then we add a half, okay, it's the same as taking 2/7 and then adding it to the sum of 3/4 and a half. And finally, given 2/5 and 3/7, we are going to conclude there's at least one rational number, which we're calling C, such that 2/5 is less than C, and C is less than 3/7. In other words, that C is between the 2/5 and the 3/7. Okay, see if you can identify these properties shown in the 3 examples. Okay, let's look at them again. Notice that 2/5 plus 0 does not change the answer, therefore 0 is the additive identity element, and this is an illustration of how the identity element operates. In the next problem, we've just changed the grouping of the numbers without changing their order, so we've associated them in different ways. This does not change the result, so this is an illustration of the associative property for addition. And finally, if we're given 2/5 and 3/7, there's at least one rational number C between them, such that 2/5 is less than C, which is less than 3/7. So remember we said, for example, for this number, all we would have to do to find it is we could just average these two here, take these two and average them, and we will get a number C, which is between them. Okay. Next question, explain why 0 doesn't have a multiplicative inverse. Well, remember that if a number has a multiplicative inverse, it means that the number, say A, multiplied by its multiplicative inverse, 1 over A, has got to produce the multiplicative identity, which is 1. So basically what we're saying is, what number could multiply by 0 to give you 1? And there is no such thing, because any number multiplied by 0 gives you 0. So we see that we cannot find a rational number C which satisfies the requirement that 0 times C would produce 1, where C then would have to be the multiplicative inverse of 0. 0 times C is producing 0. 0 is clearly not equal to 1. And so we see that there's no value of C that works, and therefore 0 does not have a multiplicative inverse. Okay, let's take a look at fractions and decimals. Really, fractions and decimals are ways that we have expressing the same idea, okay, but they look different. A fraction is an expression that indicates a quotient of two quantities, such as A over B. A is called the numerator, B is called the denominator, and the denominator can never be equal to 0. -5 over 7 is a fraction, and -5 is the numerator, 7 is the denominator. Remember now, this is really important, that the fraction can be written in 3 different ways, all with the same meaning. In this one, we've indicated that the numerator is -5 and the denominator is +7. In this one, the numerator is +5, the denominator is -7, and in this one, we've really taken +5 and +7 and negated the whole thing. They all really have the same meaning. Okay, so it doesn't matter which way you write them, they mean the same thing. So, see if we can do a little better job on this one. Okay, the negative of 5 over 7. Okay. If a fraction has a denominator that's a power of 10, then we say it is a decimal fraction. It is indicated using a decimal point. So for example, 15 over 1,000 is a decimal fraction because the denominator is a power of 10, namely 10 to the third. So we can write 15 over 1,000 as 0.015. Now let's take a look at some examples involving fractions and decimals. For example, supposing we want to change the fraction 2/7 to a decimal, correct to the nearest thousand. Well, what we really are saying is 2 is divided by 7, so it's like saying 7 into 2, and of course, in order to do this, we have to put a decimal point and then add as many zeros as we wish. Okay, here we see the division problem worked out. 7 divided into 2, and in this case, we put down 4 zeros, so we've carried the division out to 4 places. If we wanted our answer to the nearest thousandth, we simply take the last place, and if it's greater than 5, this rounds up. So to the nearest thousandth, this becomes 0.286. Let's look at the next question, writing 3.0875 as a mixed numeral in simplest form. Now remember, what this really indicates is that we have a whole number of 3, and then we're adding it to 875 10,000ths. Oh, we sort of lost it. Okay. Thank you. Right? So here we see the problem worked out. 3 and 875 10,000ths. And now, of course, this number right here can be reduced. And so we can reduce it to 3 over 400 or even 7 over 80. At that point, we can't go any further because these are in lowest terms. Let's say we want to put these numbers in order from least to greatest. Now remember that when you're dealing with the number line, going from least to greatest always works from left to right. So what you need to do is put these numbers on the number line in the correct order and then see where they fall in relation to each other. Okay. In order to do this, the easiest way is to put the numbers into decimal format, because sometimes when you look at them, for example, how are you going to relate the 3/8 to the 2/7? But if you put everything in decimal form, everything is basically in the same format that could be compared easily. So if we write 3/8 in decimal form, we have 0.375, 5/16, 0.3125, negative 1/3 as negative 0.333, and notice this bar over here means that it's repeating, and 2/7, 0.2857. So now, once you've done that, it's easy to order them from least to greatest. And you can see the order from least to greatest in decimal form here, and then finally switching back to the fractional form, we have our answer. Now, a number is called an improper fraction if it doesn't have a whole part and a fractional part. It is only a fraction. So for example, because 2 is 4/2, when we take the 4/2 from 2 and we add it to the 1/2, we get 5/2, and that is the improper fraction. The improper means that the numerator is higher than the denominator. So 2 and 1/2 would change to 5/2 in the form of an improper fraction. So see if you can change the 7 and 3/8 and the negative 1 and 7/10 to an improper fraction as well. If we look at this, we see the one we already did, the 2.5 is 5/2. The 7 and 3/8, you can think of 7 as 56/8, and then add the 3/8, and you get 59/8. Now, some of you may have learned a trick somewhere along the line, which sort of simplifies matters. You multiply the 8 by the 7, you get 56, add 3, get 59, so it's 59 over 8. What you're really doing is short-circuiting the process of thinking the 7 as 56/8, because really what you've done here when you multiply the 8 by the 7 is you've created the 56. So it's just a kind of a little bit of a short circuit to get to the answer. And then here, if we use that same short circuit, we have a negative 10 and a negative 7 added to it gives us negative 17 over 10. Now we can go backwards. We can express the improper fraction as a mixed numeral simply by dividing the denominator into the numerator. So for instance, for 15 over 4, we would divide the 4 into the 15. It's going to go 3 times because 3 times 4 is 12, and that's the closest full multiple of 4. And then you have 3 left over. So in mixed form, you would get 3 and 3/4. You see if you can do the same thing with 38 over 9 and with negative 10 over 3, and then we'll look at the results. Okay, for 38 over 9, 9 into 38 goes 4 times. 4 times 9 is 36. And we have 2 9s left over. And for negative 10 over 3, 3 goes into negative 10 3 times, or negative 3 times, really. And then we have 1/3 left over. Now, supposing we want to express these as equivalent fractions. In other words, if we have 27 over x, how is that equivalent to 9 over 1? Well, what value of x would make that equivalent? You probably can see that if x is 3, 27 over 3 is the same as 9 over 1. Now, there is, in this case, it's probably pretty obvious to you, but in the cases where it's not obvious, what you can do is treat the proportion by cross multiplication. So we have 9 times x is equal to 27, dividing both sides by 9, x is equal to 3. So the value 3 would give you 27 over 3, which is equivalent to 9 over 1. We can do the same process for the 85 over 20 equals x over 4. Or you can think of this as 4 is 1/5 of 20, so this answer has to be 1/5 of 85. And notice here, dividing both by 5, we get the equivalent value that x is equal to 17. Now, how do we compare fractions if we want to know which is larger or if they are in fact equal? What we need to do is express each fraction in terms of the same denominator, because otherwise they can't really be properly compared. So let's look at these and see how we would express them with equivalent denominators. The first case, we're trying to compare 3 over 5 to 7 over 13. Now, 5 and 13 have a least common denominator. LCD stands for least common denominator of 5 and 13 is 65. So we're going to change everything to 65ths. If we change 3/5 to 65ths, we have 39 65ths. If we change 7/13, we get 35 65ths. Therefore, 3/5, this one has a larger numerator, same denominator, so this one is the bigger fraction. And so 3/5 must be greater than 7/13. In case of 3/4 and 5/6, again, we look for a common denominator. In this case, the common denominator is 12. So we're changing everything to 12ths. 3/4 is equivalent to 9/12. 5/6 is equivalent to 10/12. And so we then have that the 9/12 is going to be less than the 10/12. So 10/12 is larger, so 3/4 is less than 5/6. Finally, looking at 2/7 and 14/49, if we change everything to 49ths rather, we see that 2/7 is the same as 14/49, and therefore 14/49 is equivalent to 14/49, and these fractions are equal. Look at the next problem. To find the sum or the difference and write the answer in simplest form. Well, in the first problem, we see that the denominators are the same. So nothing could be simpler except when the denominators are the same. Just keep the common denominator and add the numerators. On the other hand, if we have mixed forms, we have to be a little more careful. Now here, we do have the same denominator in the fraction, so we can subtract the fraction from the fraction and the whole number from the whole number. Looking at this then, 13 25ths added to 2 25ths gives us 15 25ths, and that of course can be reduced because we have a common factor of 5, so this reduces to 3/5. 10 and 5/8 less 6 and 1/8, here again, because they're all in eighths, we can just subtract the whole number portion, which gives us 4, and subtract the fractional portion, which gives us 4/8, and 4/8 is equivalent to 1/2. Let's look at finding the sums and differences, rational numbers. Now here, of course, where we have different denominators, we cannot add unless we put them over the same denominator. So 4 and 3 would have a least common denominator of 12. So we're going to have to change the 3/4 to 12ths. And we're going to have to change the 2/3 to 12ths and put the proper numbers here to make them equivalent. In this case, again, because the fractions are different, we're going to have to change to a common denominator. So we want to express 5 and 6/7 and 2 1/2 in terms of the same denominator. And in this case, the denominator would have to be 14, the lowest common denominator. So let's see how this works out. Changing everything here to 12ths means that we multiply the first fraction by 3 over 3. In other words, 1, but in the form that will give us the common denominator of 12. In this case, next problem here, we have to multiply by 4 over 4 to make the fraction come out to a denominator of 12. So now we have 9 12ths here and 8 12ths there, so then they can be added to give a total of 17 12ths. Now I have no problem with 17 12ths as an answer, okay? But if you want it in mixed form, you divide the 12 into the 17, you get 1. That's the 12 twelfths, and you have 5 twelfths left over. In the next problem, we change everything to have a common denominator of 14. So we have 5 and 12 fourteenths. And in this case, we had to multiply by 7 over 7 to give us 2 and 7 fourteenths. And now, subtracting the whole numbers, the 2 from the 5, we get 3. And the 7 fourteenths from the 12 fourteenths, we get 5 fourteenths. Okay, find the sum and difference, write the answer in simplest form. So in this case, you're trying to subtract something that's in the form of a mixed number from a whole number. Now you can do this a number of different ways, but one way might be to change everything to eighths. So you could take 1 away from the 5, make it 4 and 8/8, and then that would be easy to subtract the 1 and 3/8. So then you would have a whole number portion of 5 and a fractional portion of 5/8. Here again, because we're taking 9/10 away from 3/10 and 3/10 is smaller, we might want to change the 7 to a 6 and then add 10/10 here, so have 13/10, and then subtract the 4 and the 9/10 from that. So looking at the answers then, this is what was done. 5 was changed to 4 and 8/8, subtracting 1 and 3/8. We then get the 3 and 5/8. And here again, changing the 7 to the 6 and adding in 10 more tenths, we have 6 and 13/10, less 4 and 9/10, which gives us 2 and 4/10, or 2 and 2/5. Take this next problem, find the difference and write the answer in simplest form. Again, you can't perform this subtraction unless we have the fractional portion of the mixed number with the same denominators. So we have a denominator of 6 here and denominator of 5 there. So the least common denominator will be 30. So we can change this to 30ths, 15, and 5/30ths, and then subtract 8 and 24/30ths. Now, here again, you see there's an issue because the 24/30ths is larger than the 5/30ths, but we can fix that by adding 1 to this. So get rid of the 15, change it to 14, and then we have 35/30ths, so we can easily subtract the 24/30ths. And you see that's what happens here. So we have 15 and 5/30ths, less 8 and 24/30ths. We've made the conversion, taking one whole number away from the 15 to make it 14, and changing the 1 to 30ths. And then the 24/30ths can subtract from the 35/30ths to give us 11/30ths, and the difference between the 8 and the 14 gives us our 6. Okay. Next, let's look at the multiplication of these rational numbers. Now, in multiplication, generally speaking, it'll always work if you multiply across the top and multiply across the bottom. It might not give you the lowest answer to start with, but it'll always give you the right number. So if we did that, we would have 21 over 84. And then we could reduce that. But we also have the option, if we see that, for example, we know the numbers on the top are going to wind up on the top of the answer, the numbers on the bottom are going to wind up in the bottom of the answer. So we can always think of this as the 7 is going to multiply the 3, the 12 is going to multiply the 7, and so we can basically divide out from numerator and denominator, what we sometimes refer to as cancellation, divide out the 7s, and we also have a 3 and a 12. We can divide 3 into itself and 3 into 12, and wind up with the common fraction 1/4. Okay. Here again, in the multiplication, we see that we're multiplying a number by its multiplicative inverse, so that should give us 1. So let's take a look. Okay. Notice here, the 7s cancel, the 3 goes into the 12 4 times, we wind up with 1/4. And here we have 12 over 12 or 1, or you can just recognize that we have the reciprocals, and therefore a number multiplied by its reciprocal or its multiplicative inverse, which is in our fancier language, number multiplied by the multiplicative inverse is going to give you the multiplicative identity, namely 1. Okay. To perform the multiplication and simplify, the easiest way to do the multiplication is to change the 3 1/4 into an improper fraction. So this gives us 13 over 4, which we then can multiply by 20, which is like 20 over 1. And the 4 can divide into the 20, and we wind up with 65. I guess if I lean on this screen too heavily, it winds up advancing, so I'm sorry about that. Okay, so let's take a look. Doesn't want to advance. Finally. Okay, now in this particular case, they actually, whoever worked out this solution, actually multiplied the 13 by the 20 to give 260 and the 1 by the 4 to give 4, and then reduced it. But we could see that you could have reduced it here by dividing the 4 into the 20, and that would have given you the 65 over 1, or just 65 in a simpler way. Okay. Whoops. Did I get ahead of myself here? Okay. All right, we want to perform this multiplication and then simplify the result. All right, again, probably better to change everything into the form of an improper fraction. So we have 3 times 5 is 15, plus 1 is 16. So we get 16 over 3. It's not supposed to... 16 over 3, and then here we have 12 plus 3 is 15 over 4. So we have 16 over 3 times 15 over 4. Again, assuming we're not working with calculators, in which case you don't particularly care how simple it is for starters, but if you're doing mental arithmetic, you probably would like to make this simpler. So we could divide the 4 into the 16 and the 3 into the 5. We now have a denominator of 1 and a numerator of only 20. And we see that this is the result that we get. Okay. Now remember that division is the same as multiplication by an inverse. So if we are dividing 3/7, in this first case, 3/7 by 7/3, it's the same as multiplying 3/7 by 3/7. And so the answer is going to be 9 over 49. Now, notice in the next one, 3/7 divided by 3/7, we can go through the routine of changing it to a multiplication, multiplying by the inverse, and then canceling the common factors and getting 1. But what you really should notice is that when a number is divided by itself, it's always going to give you 1. Okay. Any number divided by itself is 1. So it doesn't matter how complicated it is to start with. If you're dividing the number by itself, you're going to get 1. Now, perform the division and simplify completely. We have 10 over 1 divided by 2.5. You really have to think of the 2.5 as 5 halves. So if we have 10 divided by 5 halves, that's the same as 10 multiplied by 2/5. Now we can also do some cancellation here, dividing out common factors. Remember, cancellation is just a loose term for dividing common factors, and the net result is 4 over 1, or just 4. Taking a look at the next problem, simplify and write as a mixed numeral. We have 4 1/4 divided by 1 1/2. Again, it's going to be much easier to work with these if you treat them in terms of common fractions. So the first one, we're going to have 16 plus 1 17/4. Okay, and then divided by 1 1/2. So this is 17/4 divided by 3 halves is the same as 17/4 multiplied by 2/3. Now the 2 can divide into the 4, and so we're going to wind up with 17 over 6. And again, as far as I'm concerned, 17 over 6 is a perfectly good answer, but if for some reason you need it in mixed form, you divide the 6 into the 17, which will give you 2 because you have 12. 6 into 17 goes into 12, and you have 5 left over. So 2 and 5, 6. A little trouble here. A little difficulty here. Right. We want to write each fraction as a decimal. Okay. In other words, it's still a fraction, but it's written in the form of a decimal. So 3/10, 7/1000, 17 over 100. These are very simple because when we have powers of 10 as our denominator, then we just can really just do it mentally. So we take a look. 3/10 is the same as writing 0.3. 7/1000 is the same as writing 0.007. And 1700ths the same as writing 0.17. Now, I want you to notice that in each case, we've put the 0 in before the decimal point. It's true that this means the same thing as this, but this is much easier to understand. And if you write it in this form, you're less likely to make an error in reading it. And that could be terribly important if you're working in the medical field, because you're working with drugs, you're working with dosages. You want to make sure that you read everything correctly. So being sure that you have the decimal point in the right place is very important. So we're going to make a point of always putting the 0 in front of the decimal point so we very clearly see what's going on. Okay, now we want to write these as fractions in simplest form. The first one, if we read it out loud, we read it as 35/100. So we're really reading it as a fraction, 35/100. Now, of course, that can be reduced by dividing by 5. And so in reduced form, we get 7/20. Now you try and see if you can do parts B and C following the same idea. I'll give you a few moments to do that. And now let's see what we come up with. Okay, we've taken a look at this one already. This gives us 10 over 1,000, and we can reduce that to 1 over 100. And here we have 1 and 25/100, or a total of 125/100. 1 and 25/100, and the 25/100 reduces to 1/4. So you can write it as 1 1/4, or you can write it as 5/4. Which form you use is very much going to depend upon what you're trying to emphasize in a particular problem. All right, next, we want to take a look at a combination of operations. In order to add these, we have to make sure we line up the decimal point. Okay, so if we have 3.04 and we're trying to add it to 14.2, right? And then we want to add that to, then subtract 7.089. The idea is we have to line up the decimal point. So first we see the 3.04 added to the 14.2 with the decimal points lined up, 17.24. Now in order to subtract the 7.089, notice we added the 0 here. Doesn't change the meaning, but it gives us the place that we need. Subtracting the 7.089 from the 17.24, we get 10.151 as our final result. Now in this question, 2.37 times 5.2, I just want to make a point again about the idea of having some kind of mental sense before you do problems of what the answer is likely to be. All of you probably use calculators these days, and most likely you're not going to be doing the problems we've been discussing by simple arithmetic. Probably we'll be using even just 4-function calculators to do problems like this. The issue is that the calculator becomes a kind of Bible for everybody. And, oh, well, it said this on the screen, so it must be right. But it is possible to type in something incorrectly and come up with the wrong answer. So it always makes sense, even if you're doing something fairly simple on a calculator like this problem, to think in advance, what should the answer look like? About how much should I get as my answer? So here we have a number that's a bit more than 2 and a number that's a bit more than 5. Now 2 times 5 would be 10. So we expect a number that's going to be greater than 10, but it's not going to be a whole lot greater. You know, maybe since we're dealing with about a third here and about 1/5 there, you know, a little bit bigger, maybe like something around 12. So if we take a look at the answer, notice that we actually perform the operation, either changing to fractions the way we did here, and then using multiplication of fractions, or multiplying them in decimal form. We wind up with 12.324, which makes sense. Now, if you do this on a calculator, of course, it'll save you a lot of time, but you should still have that idea in your head. This is going to be something larger than 10, maybe 12-ish. And so when you see the answer, you know that this answer makes sense and it's reasonable. And it's always important to be thinking about whether your answers are reasonable. Okay. Perform the division, 2.4 divided by 0.015. So we're doing this. Now remember that when you're dividing the decimal, what you have to do is, if you're doing it longhand, you have to move this 3 places. So we have to move this 3 places to change these to whole numbers. So we wind up with 24/10 multiplied by 1,000 over 15. Remember, divided by 15 over 1,000 is the same as multiplying by the reciprocal. We can do this in the form of fractions and then reduce. Or we can actually do the long division, if you remember that fairly tedious method of doing long division, and get the answer that way. Or if you have a 4-function calculator, you can do with a 4-function calculator. Just keep in mind, trying to make sure that the answer you get seems reasonable. Now we want to look at changing rational numbers or ratios to decimal form. So for example, supposing we want to change the rational number 12 over 5 to a decimal format. Okay. What we're really saying when we say 12 over 5 is that 5 should divide into 12, the way we have it here. So dividing the 5 into the 12 using your standard forms of division, we get 2.4. 2.4 is what we call a terminating decimal. Remember, termination means to end. So if the decimal ends, it has the fancy title, terminating decimal. Now, sometimes we get a non-terminating repeating decimal. Okay. A non-terminating repeating decimal is also going to be the result of dealing with a rational number or a ratio. We spoke about this earlier. Keep in mind that if it's a repeating pattern, even if it doesn't end, it is going to be expressible in the form of a common fraction. Okay. Let's consider now the terminating decimal, 32 hundredths, and trying to put it back into the form of a ratio. Now we're going back the other way. We have 32 hundredths is a terminating decimal. It's read as 32 hundredths, so what it means is 32 over 100. If we simplify that by dividing by common factor of 4, we wind up that 32 over 100 is the same as 8 over 25. Now let's take a look at a non-terminating repeating decimal, 7/10. Okay, and see how this can be put into the form A over B, where B is not 0. Okay, so we take the repeating decimal 0.7, or continuing. That means 0.7777 going on indefinitely. If we multiply both sides of this equation by 10, taking this equation and multiplying both sides by 10, notice you get 10 times x is 7.7, and then the 7 part, the decimal part, just keeps repeating. So if you subtract this fraction, 1, from 2, in other words, what we're doing is we're taking 10x equals 7.7 with the 7 repeating, going on forever. and then x is just 0.7 repeating forever, this part's going to drop out. And so we're going to wind up with 9x equals 7, and so x is equal to 7 over 9. So we see that the repeating decimal winds up being expressible in the form of a common fraction, a rational number. Well, we've spoken an awful lot and done a lot of problems with rational numbers, or numbers that can be expressed as ratios. Now we want to look at the numbers that cannot be expressed as the ratio of two integers, numbers that we call irrational numbers. Remember, I said these are irrational doesn't mean that they're not sane. It just means that they can't be expressed as ratios. Irrational numbers are numbers that cannot be written in the format a over b, where a and b are integers and b is not 0. If we take the set of real numbers and we subtract the rational numbers, then what's left are the irrational numbers. And we denote these irrational numbers by q with a bar over it. When you expand an irrational number into decimal form, you get a non-terminating, non-recurring, or non-repeating decimal form. The irrational number can be positive or negative. So what are some examples of irrational numbers? Well, numbers like radical 3, negative of radical 10, the number pi, which I'm sure you're familiar with, and numbers like this. Now, you might say to yourself, well, there is a pattern there. Well, yeah, there's a pattern, but it's not the same pattern. This pattern, 0.154, the next time around, we've added another 4, and the next time around, we've added still another 4. In order for this pattern to be repeating, it would have to be 154, 154, 154 on indefinitely. And of course, if you have a decimal fraction which just has a whole bunch of numbers that never repeat and have no particular pattern at all, that's clearly an irrational number. Now, what properties do these numbers have? Well, again, we have density. Between any two real numbers, they're going to be an infinite number of irrational numbers. Irrational numbers can be placed in order on a number line. Now, you might say, well, all numbers can be placed on order on a number line, but that's actually not true. We spoke way in the beginning about complex numbers, and we said, well, we really weren't going to deal with them very much because they couldn't be put on the number line. And they not only can't be put on the number line, they can't be ordered. So you will, if you get to a point where you're studying complex numbers, you'll see that they don't behave the way the rationals and irrationals do. They cannot be put in a kind of size place or ordered. The rational numbers, along with the irrational numbers, are what make up the set of real numbers. So if you have a number line, the number line is going to be completely filled with rationals and irrational numbers, and there's no space for anything else. The number line is complete once we have rationals and irrationals together on it. Every irrational number will correspond to one and only one point. That's a unique point, means one and only one on the real number line. And every point on the real number line will correspond either to a unique rational number or to a unique irrational number. And the set of irrational numbers is not closed under addition, subtraction, multiplication, or division. It's very easy to show with a simple example. For example, say we look at radical 3 and we multiply by radical 3, we get 3. So we see that it's very easy to demonstrate a counterexample. And remember, if we want to show that something is not true, the easiest way is to deal with a counterexample. Now, when we take these rational numbers and we take the irrational numbers and we smush them all together, form the union of the set of rational numbers and irrational numbers, then this is what gives us the set we call real numbers. And these are really the numbers that we work with in virtually everything that we do. So the real numbers have the following properties. And much of what we saw for the rational number summary is the same here. They have density. For any two real numbers, there's going to be at least one real number lying between them. And again, you can show this by simply averaging them. The real numbers have a property we call completeness. They completely fill the number line, meaning once the real numbers are on the number line, there's no place to put anything else. Any other number that exists, like complex numbers, we have to deal with in a whole other way. They can't go on the number line. The real numbers are closed under the operations of addition, subtraction, and multiplication, meaning that the sum or difference of real numbers is a real number, and the product of any two real numbers is a real number. We also have an associative or grouping property under addition and multiplication, just as we did for the rationals. So if we group this A plus B plus C by grouping the second pair first, it's going to give us the same result as grouping the first pair. And then also in multiplication, the same thing holds. If we group B and C together, A multiplied by the result of B and C is the same as first multiplying A by B and then multiplying it by C. And again, commutation, like going back and forth to work, they work in both directions. A plus B will give us B plus A. And I think this was supposed to be A times B. I have a little error here in the PowerPoint. A times B equals B times A. So we have for addition and for multiplication over here. Real numbers exhibit a distributive property of multiplication over addition. So for any real numbers A, B, and C, A times the sum of B and C is the same as A times B plus A times C. There is an additive identity element 0, as there was for the rationals. For any real number A plus 0 is A, and 0 plus A is A. Every real number has an additive inverse. The additive inverse of A is negative A, or the opposite of A. Okay. We can consider the additive inverses as opposites. A added to the opposite of A is the same as the opposite of A added to A, and that gives us 0, the identity element. There's a multiplicative identity of 1 for any real number, A multiplied by 1, and 1 multiplied by A just doesn't change anything. It gives you the identical thing you started with, that's A, hence we call it an identity. Multiplicative property of 0, 0 basically wipes everything out to 0. You multiply anything by 0, you get 0. A times 0 is 0, 0 times A is 0. And multiplicative property of negative 1 for any real number A multiplied by negative 1 is is negative A, and A multiplied by negative 1 is the opposite of A. These both say the same thing. Again, I think we have an error in the PowerPoint here. We want to write A times negative 1 is negative A, and negative 1 multiplied by A is negative A. And every number except 0 is going to have a multiplicative inverse, which is something we call its reciprocal. For any real number A, as long as A is not 0, there's a real number 1 over A, such that A times 1 over A gives you the multiplicative identity, which is 1. And if there are real numbers A over B, where both A and B are not 0, then there must be a real number B over A, which when multiplied produces the identity. So this B over A would be called the reciprocal of A over B, or the multiplicative inverse. So multiplicative inverse is the fancy name for reciprocal. Okay. So now let's take a look at some problems involving using the real numbers. First question: what is the additive identity element and the additive inverse of the number negative 3 over 7? Okay. The additive identity, remember, is going to be the number which adds to this number. The additive identity element is going to be the element which adds to this number without changing it, and the additive inverse will be the number that adds to this number to produce the identity element for addition, which is 0. So taking a look now, the additive identity element is 0 because negative 3/7 added to 0 isn't changed. We still have negative 3/7. And the additive inverse is positive 3/7 because negative 3/7 added to positive 3/7 produces the identity element 0. Okay. Looking at these, identify the property that's illustrated in the problem. Now, if we look at this problem, we see we have 6 plus x. Here we have x plus 6. Okay, so these have been reversed. And so we are dealing now with addition under commutation, commutative property. Here, we're multiplying negative 4 by -1, the result is going to be +4. And in this case, we see the distribution of 3, multiplication distributing over, you can think of it as the addition of -8 or subtraction of 8 from P. Okay, so first, commutative property for addition. Second one shows us the multiplicative property of -1. Okay, changing it to the opposite. And finally, the distributive property of multiplication with respect to, you can say addition because it's addition of a negative, or you can say over subtraction, it doesn't matter. This question asks us to show that subtraction is not a commutative property in the set of real numbers. Okay. If we look at this, all you need to find, remember, to show that something is not true is to find one counterexample. Always easier to show something is not true than to show that it's true. To show it's true, you have to prove everything works. To show it's not true, just need to show one thing doesn't work. Okay, so the question is, does 5 minus 7 give us the same result as 7 minus 5? Well, 5 minus 7 gives us a -2. 7 minus 5 gives us a +2. Clearly, they're not the same, so subtraction is not a commutative property. Did I go backwards here? I think I did. I think we did this already, right? Yeah. That one too. Okay. So finally, we're going to look at the notion, which is extremely important, the notion of absolute value of a number. The absolute value of a number tells us how many units that number is away from 0 when you place it on a number line. So in terms of absolute value, it doesn't really matter whether you're dealing with going to the right or going to the left. What matters is how far away are you from a starting point at 0. The symbol for absolute value is a vertical bar on each side of the numeral. So here, absolute value of x is written this way, x with vertical bars around it. If x starts out as a positive number, then the absolute value of x, or the distance it is away from 0, is just the same as the number you started with. So for instance, something, if we say absolute value of 5, it's just going to be 5. And similarly, if we deal with the absolute value of 0, it's just going to be 0, because it's just the same as what we started with. But supposing we start with the absolute value of, say, -5. Well, -5 is 5 units away on the number line. It's 5 units away from 0, and that's what we're looking for. How far away is it from 0? We don't care the direction right now. We care how far is it from 0. -5 is also 5 units away from 0. So the absolute value of -5 is 5. The definition says that the absolute value of x is the same as x. You can read this as same as x if x is greater than or equal to 0. And in this case, I would read the negative as opposite rather than saying negative. Say the absolute value of x is the opposite of what x is if x is a negative number. So when x was -5, its absolute value was its opposite, which was 5. Okay. If we graph the absolute value function, we see that if x is greater than or equal to 0, we're just going to have the line y equals x. If x is less than 0, the line is going to be the line for the opposite of x. So together, we get these two pieces that form the absolute value function. Notice that the y values here are all above the x-axis. We always get a positive result when we take the absolute value of a number. Okay, so for instance, let's take a look. Find the absolute value. Find the value of this expression. The negative of the absolute value of 5, add it to the absolute value of -4, and then subtract the absolute value of -3. Well, the absolute value of 5 is 5, so we have the opposite of 5. We're adding that to the absolute value of -4. The absolute value of -4 is 4, so we're adding that to 4. And then we're subtracting the absolute value of -3. The absolute value of -3 is 3. So when we drop the absolute value signs, this is what we get. When we combine these, we have -1 and a -3, and the net result is a -4. Here. Now we want to look at solving an absolute value equation. This equation says the absolute value of some number represented by x minus 3 is equal to 8. Well, we don't know whether this number is non-negative or negative. Now, if the number is non-negative, then we don't need the absolute value sign. We just have x minus 3 is equal to 8. But if the number is negative, then it's its opposite, which is equal to 8. In other words, the opposite of this number equals 8. So we carry through this solution, okay? If this is positive, we have that x minus 3 is equal to 8 and x is equal to 11. But if it's negative, it's its opposite, which is equal to 8. So x minus 3 must be -8 and x would be -5. Therefore, the solution set in this case consists of the elements -5 and 11. And if you go back and you check, which is really important because the absolute value equations can sometimes, throw people off a little bit. Go back and check your answers. If you put 11 in here, you have 11 minus 3 is 8. Absolute value of 8 is 8, so that checks. If you put -5 in there, you get the absolute value of -5 minus 3. That's the absolute value of -8. The absolute value of -8 is also 8, so that checks as well. So checking these is very important in the case of absolute value equations. If you do that, you probably won't go astray. Okay. Next question, explain why the absolute value of x is minus x when x is negative. Well, remember we said think about this as opposite. Okay. If x is a negative number, its absolute value is positive, so it's the opposite of what x is. We represent the opposite with a negative sign. So remember, we're really looking for the opposite of x. So if x is negative, you need to multiply by -1 to change the value to its opposite, namely the positive value. I think we're back home again. I think we're back to the beginning. So I want to discard the notations. And let me just point out a few things to you that you need to know. You may find it a little bewildering to have gone over all of this in such a short period of time. But I want to remind you that there is support available for you. You have support at learnamerica.com. And also you can ask me questions by sending me an email. My email is Susan, I'll write this out for you. Susan T at learnamerica.com. Oops. Very sensitive thing we have here. And these videos and PowerPoints for this session are available within 24 hours at the Teacher's Corner section in the nursing portal. And if you have other questions, apparently you got an email last Friday, and you can read the email for questions that you might have about other aspects of the program. So thank you very much, and hope to see you at the individual support sessions.